So the next unit we're going to be working on is called Chemical Formulae, Equations and Calculations. So the learning objectives for this unit are to be able to use molar gas volume, to define what the mole and Avogadro's constant is, calculate reacting masses given data, calculate percentage yield, understand how the formulae of simple compounds can be obtained through experiment, define the terms empirical and molecular formulae, calculate empirical formulae from data, and calculate stoichiometric reacting masses, volumes of gases in solutions, and concentrations if given values. And finally, calculate the molecular formula from relative atomic masses. So the first thing we have to consider is, what is this thing called the mole? So the mole essentially is a counting unit. It is similar to a dozen, except instead of the number 12 for a dozen, it's 602 billion trillion. Quite a large number. And it can be written easily, or more simply, as 6 times 10 to the 23, which is known as the scientific notation. And it was named after this man here, Avogadro. Okay, so it's called Avogadro's number. So just how big is this mole? Well, if you had enough soft drink cans to cover the surface of the Earth will be covered to a depth of over 200 miles. If you had Avogadro's number of unpopped popcorn kernels and spread them across the US of A, the country will be covered to a depth of 9 miles. And if you were able to count the atoms at a rate of 10 million per second, it would take about 2 billion years to count the number of atoms in 1 mole. Okay, so it's actually a very large number. So let's see how much you've learned about what a mole is. So suppose we invented a new collection unit called the Chinooga. One Chinooga contains 8 objects. So how many paper clips are in one Chinooga? Pause the video now and see if you can get the correct answer. Okay, so you should have come up to the answer as being C. Okay, one Chinooga would contain 8 paper clips. How many oranges are in 2.0 Chinooga? Again, pausing the video and seeing what you can come up with. Okay, the answer is, of course, 16. One Chinooga is 8, so 2 times 8 is going to be 16. And finally, how many Chinooga contain 40 gummy bears? Well, if you know that one Chinooga contains 8, then 40 gummy bears must consist of 5 Chinooga. So the answer is A. Okay, so with that learning check now complete, hopefully you got 100%. We're now just going to watch a quick video on what is the mole.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So, just reinforcing that, the mole. So 1 dozen cookies will equal 12 cookies. 1 mole of cookies will be 6.02 times 10 to the 23 cookies. Quite a lot of cookies. 1 dozen cars, 12 cars. 1 mole of cars, 6.02 times 10 to the 23 cars. 1 dozen aluminium atoms equals 12 aluminium atoms. 1 mole of aluminium atoms equals 6.02 times 10 to the 23 atoms. So you're getting the idea of what a mole is. So note that the number is always going to be the same, okay, but the mass is very different. So the mass of 6 times 10 to the 23 atoms is not going to be the same as a mass of 6 times 10 to the 23 cars. The mole can be abbreviated to mole without the E, so we save some time writing. So the mole of particles contains 6.02 times 10 to the 23 particles. 1 mole of carbon will equal 6.02 times 10 to the 23 carbon atoms. 1 mole of water will contain 6.02 times 10 to the 23 water molecules. And 1 mole of sodium chloride will contain 6.02 times 10 to the 23 sodium chloride molecules. I say the word molecules because really it's a giant lattice, as we learned last year when we looked at ionic bonding. It's just the simplest ratio, because it'll consist of 6.02 times 10 to the 23 sodium ions and 6.02 times 10 to the 23 chloride ions. So let's have a learning check. So what are the number of atoms in 0.5 moles of aluminium? Okay, so pause the video now and see what you come up with. Okay, so 1 mole of aluminium is going to contain 6.02 times 10 to the 23 aluminium atoms, so half a mole will be C, 3.01 times 10 to the 23 aluminium atoms. number of moles of sulfur in 1.8 times 10 to the 24 sulfur atoms. Okay, it's going to be number of moles, it will be 3 moles of sulfur atoms. Okay, so 6 times 10 to the 23 is 1 mole, so you have to divide this number by a mole to give you the number of moles of sulfur atoms. So let's look at molar mass of molecules and compounds. So let's consider, for example, calcium chloride. What is the molar mass of calcium chloride? So the mass in grams of 1 mole equals numerically to the sum of the atomic masses. Okay, so 1 mole of calcium times 40.1 grams per mole, which you get from the periodic table, plus 2 moles of chlorine, which are equal to 35.5 grams per mole each. So it gives you total mass of 111.1 grams per mole of calcium Cl2. Okay, and we can of course use questions, okay, around this, and you can use an equation, which you have to memorize. And the equation is, let's go back again, there we go, the mass will be equal to the number of moles divided by the molar mass of atoms. Or the number of moles can be calculated from the mass, using the molar mass. Number of moles equals mass over mR. That's an important equation to remember. So how do you convert moles and grams? Well, here's a question to answer using the equation I've just provided. Number of moles equals mass over molar mass. So aluminium is often used for the structure of lightweight bicycle frames. How many grams of aluminium are there in 3 moles of aluminium? So pause the video now and have a go. Okay, so you should have got 3 moles of aluminium equaling 81 grams. This is how you do it. So 1 mole of aluminium is equal to 27 grams per mole. Moles of aluminium, 3 moles. So mass equals number of moles times molar mass. So 3 times 27. So in total, 81 grams of aluminium. Okay, another learning check. Artificial sweetener aspartame, also known as NutraSweet as its brand name, has a formula C14H18N2O5 and is used to sweeten diets, foods, coffee and soft drinks. How many moles of aspartame are present in 225 grams of aspartame? So pause the video now and see if you can work it out, and then I'm going to grab a calculator and also work it out with you. Okay, so the equation that of course you're going to use is going to be the old special number of moles equals mass over the molar mass, okay, M over MR. So we just have to find the mass, okay, we do have that, so we're given the mass and it's 225. We don't know the molar mass, and the way we get the molar mass is we have to add up all the atomic masses of aspartame. So here we go then. Okay, so the molecular molar mass of NutraSweet is going to be 12 times 14, okay, that's the carbon, plus 1 times 18, okay, the numbers are going to be a bit easier for that, plus 2 times nitrogen, which if you look at the periodic table, is going to be 14 plus, what is that? Just rub that out slightly, 5. Okay, so 5 times 16. Okay, so that will equal, 12 times 14 is going to be 160 plus Maths is easy on that one. 18 plus 28 plus 5 times 16. There we go. Which equals, okay, so here we go. 28 plus 18 plus 160 plus 80 equals 286. Okay, and the number of moles therefore will equal the mass 225 divided by 286, which equals 0.8 moles. And that is the answer. So hopefully you got the correct answer for that question. Okay, so you also have to be able to read equations using moles. So here's an equation: calcium reacting with sulfuric acid to form calcium sulfate salt plus hydrogen gas. Okay, so that really can be read as one amount of calcium reacts with one amount of sulfuric acid to give one amount of calcium sulfate and one amount of hydrogen gas. And the amount we use is the mole, and now the reaction can read as 1 mole of calcium reacts with 1 mole of sulfuric acid to give 1 mole of calcium sulfate plus 1 mole of hydrogen gas. Okay, that's what that reads as a chemist. There we go, a little flip there for you. Right. So the questions are, if we have 1 mole of calcium, how many moles of sulfuric acid are needed to fully react the calcium? Okay, so again, pausing the video and seeing if you get the correct answer. Okay, you should have got 1 mole. Okay, because it's a 1-to-1 ratio. It's all about ratios. If we had 0.5 moles of calcium, how many moles of sulfuric acid would this be required to use? Again, it would be half a mole. Okay, because you've got half a mole, it's a 1-to-1 ratio. So if you divide 1 by 2, you've got to divide the other side by 2. And finally, if 0.5 moles of calcium reacted with 0.5 moles of sulfuric acid, how many moles of calcium sulfate and how many moles of hydrogen gas would be formed? And you should have got the same answer, 0.5 moles of each. So reading again equations from moles, equations are so very useful. Some more questions. Okay, that was from last slide, so 0.5 moles of hydrogen gas and 0.5 moles of calcium sulfate. And given the associated molar atomic masses of these values, work out the molar masses of sulfuric acid, calcium sulfate, and hydrogen. Okay, so pause the video now and see if you can get the correct answers. Okay, so sulfuric acid should be 2 plus 32 plus 16 plus 64. So 64 plus 32 plus 2, so you should have got 98 for sulfuric acid, 136 for calcium sulfate, and hydrogen. I can do that. 1 plus 1 equals 2. Okay, and using those values, calculate the mass of hydrogen gas and the mass of calcium sulfate formed in this reaction here when you've got these values for the moles. Okay, so you should have got 1 gram of hydrogen and 68 grams of calcium sulfate, basically half the molar masses. So here's a new reaction. Now we've got iron oxide reacting with carbon monoxide to give iron and carbon dioxide. If 200 grams of iron oxide is reacted with what mass of iron is produced? And we've even given you the molar masses for the molecules. Okay, so again, pausing the video to see what answers you get. Okay, so we can see that every mole of iron oxide reacts with 2 moles of iron that are formed. This means that we can find the number of moles of iron oxide. We can then work out the number of moles of iron, and then correspondingly the mass of iron. Okay, and that's how we work it out. The moles of iron oxide will equal the mass of iron oxide divided by the molar mass of iron oxide, which will be 1.25 moles of iron oxide. And since we know the ratio is going to be 1 to 2, we can then work out the amount of moles of iron oxide that are formed. You get 2.5 moles of iron formed, and now you have to work out the mass of iron. So Work out the number of how many millimoles of hydrochloric acid are used to completely react 60 grams of magnesium metal in the following reaction. So what I would do is I'd draw a grid. Okay, so you have down the one side of the column, you'd have mass, or molar mass, sorry, the mass, number of moles, and the reaction ratio. So for magnesium, the mass is molar mass is 24 grams per mole. The molar mass for hydrochloric acid is 36.5 grams per mole. The mass is 60 grams for magnesium. So you can work out number of moles because it's going to be moles over molar mass, or 2.5 moles. So the ratio from the equation is given as 1 to 2. Okay, so 1 to 2. So you can therefore work out the number of moles of hydrochloric acid working backwards, because it's going to be twice the number of moles of magnesium. Okay, so you've got 5 moles of hydrochloric acid, which is going to be equal to 183 grams of hydrochloric acid. So what was the mass of hydrochloric acid used? Okay, did we get that number? Well, it's going to be 5 times the molar mass, 5 times 36.5, or 183 grams if you go to 3 significant figures. So this here is all your triple award stuff. Okay, concentration. So particles per volume. So can be in grams per litre, but chemists, we like to have them in moles per decimeter cubed. And they're related to the formula. C equals N divided by V, which is really small, where N equals number of moles, V equals the volume in decimeters cubed, and concentration is in moles per decimeters cubed. So write the formula for the moles of using mass and molar mass, and now write the concentration using volume and moles, the equations. Okay, so that is the number of moles, it's mass divided by molar mass, and this is the equation that we've just been introduced to. Concentration equals number of moles divided by a set volume. So here's an example. You've got 15 grams of sodium chloride and it's dissolved in 1 decimeter cubed of water. What is the concentration, I hear you say, of the solution in moles per decimeters cubed? And the molar mass is given of sodium chloride of 58.5 grams per mole. So first, find the moles of sodium chloride. So number of moles equals mass over molar mass, which equals 15 divided by 58.5, or 0.2564 moles of sodium chloride. Then we divide the moles by the volume in decimeters cubed. Okay, we have 1 decimeter cubed, so that's easy. It'll be equal to 0.256 moles per decimeters cubed, because the volume is 1 decimeter cubed. So here's another example. 20 grams of sodium hydroxide is dissolved in half a decimeter cubed of water. What is the concentration of the solution in moles per decimeters cubed? Okay, now I want you to pause the video and see if you can work it out for yourself. Then come back and you'll see if you've got it correct. Alright, so the molar mass of sodium hydroxide is 40 grams per mole. Okay, you can work that out from the periodic table that you'll be given. Find the moles of sodium hydroxide first. Okay, so number of moles equals mass over molar mass, or 20 divided by 40, or half a mole. And then you divide the moles by the volume, which is in decimeter cubed, which is 0.5 decimeters cubed. So it's going to be 1 mole per decimeter cubed. So hopefully you got the correct answer there. So now you have a go. Calculate the concentration of 18 grams of glucose C6H12O6 dissolved in 200 centimeters cubed of pancake syrup. Okay, let's see what the answer is. The answer is going to be number of moles equals mass over molar mass, 18 divided by 180, which gives you 0.1 moles of glucose. And then the concentration is going to be concentration equals number of moles divided by volume, or C equals 0.1 divided by 0.2. And you have to be very careful with converting. Notice I've converted the centimeters cubed into decimeters cubed. So it gives you a final concentration of 0.5 moles per decimeter cubed, which is the correct answer. Okay, so we've looked at solids, we've looked at liquids, and now we're just going to finish off by looking at calculating moles in gases. So the density of a gas is much less than a liquid. We can calculate the density of any gas at room temperature and standard room temperature and pressure, known as RTB. 1 mole of gas occupies a volume of 24 decimeters cubed, or 24 litres, at the standard room pressure and temperature. So 1 atmosphere, usually at 1 atmosphere and 24 degrees Celsius. So room temperature and room atmosphere. Okay, and the equation for the volume of the gas at RTP is volume at RTP is number of moles times 24. That's it, number of moles times 24. So the formula of a number of moles in RTP is the volume of gas divided by the molar volume in decimeters cubed, which is 24, equals the number of moles. Okay, you have to know that. So let's try using it now. Calculating the moles of gases example. So how many moles are in 3 decimeters cubed of ammonia gas, NH3, at RTP? So again, pausing the video and seeing if you can work it out for yourself. Right. So the molar volume of ammonia at RTP, we already know is set. It's 24 decimeters cubed per mole. Number of moles, we're going to be, through that equation, the volume of the gas divided by the volume of 1 mole of that gas. It's going to be 3 divided by 24, or 0.125 moles of ammonia. And that's the answer. So what happens if you have a volume of a gas of a known mass? So what is the volume of 1.96 grams of carbon dioxide occupies at room temperature and pressure? So I want you to pause this and just see if you can work it out for yourself. You might have to be using a combination of equations. And then I'm going to come and show you the answer and see if you're on the right track. Right, so we want V, however, we don't have V, we don't have a volume, we have number of moles. So we need to first work out the number of moles. So the number of moles equals the mass over the molar mass. So it's going to be the mass, 1.96 grams, divided by the molar mass of carbon dioxide, which is 44. So now we have the number of moles of carbon dioxide. Okay, but we still want V, we only got N. So how are we going to do that then? V equals number of moles times 24, because you're at standard room temperature and pressure. So it's going to equal 0.045 times 24, which equals 1.08 decimeters cubed, about a litre. So now we have 4 interpretations for the mole. 1 mole equals 6.02 times 10 to the 23 particles, or Avogadro's number. 1 mole equals mass divided by molar mass. 1 mole equals 24 decimeters cubed at standard room temperature and pressure for at least a gas. And for liquids, 1 mole equals volume times concentration. So now we can use these to solve our problems. This gives us 4 units to use to convert between moles, particles, mass, and volume, which is a great advantage. So, what is the mass of 3.36 decimeters cubed of ozone gas, O3, now at room temperature and pressure? So pausing the video now, seeing if you can work it out for yourself. Okay, so we want the mass of ozone, but we only have the volume of ozone. So we've got to convert volume to moles and then moles into mass. So number of moles equals volume divided by 24, which we already know. So therefore 3.36 divided by 24 should give us the number of moles. So we now have 0.14 moles of ozone. Okay, so we're on the way. We now have number of moles of ozone. We also know that the mass equals number of moles times the molar mass, which is going to be equal to 0.14 times 48, because ozone's molar mass is going to be 3 times oxygen. So it's going to be 16 times 3, or 48, which gives us the answer of 6.72 grams of ozone. And percentage composition is also quite powerful in chemistry, because it allows us to calculate the simplest ratio amongst those atoms found in a compound. And that's essentially what an empirical formula is. An empirical formula is the formula of a compound that expresses the lowest whole number ratio of atoms in that compound. Okay, so and a molecular formula is the actual formula of the compound showing the number of protons present. Okay, so as examples, we have C4H10 is a molecular formula, whereas C2H5 would be the empirical formula, because it is the lowest whole number ratio of the atoms present. C6H12O6, or glucose, is the molecular formula, and CH2O is the empirical formula, the simplest ratio of the molecular formula. So in terms of formula, is hydrogen peroxide's H2O2 an empirical formula or a molecular formula? Well, it's going to be a molecular formula because you can divide both sides by 2 to get OH, which is the empirical formula. So how do we calculate empirical formula? Well, let's give an example. An oxide of aluminium is formed by the reaction of 4.15 grams of aluminium and 3.692 grams of oxygen. Let's calculate the empirical formula. So the first thing you have to do is you have to determine the number of grams of each element in the compound. Okay, so you've got 4.15 grams of aluminium and 3.692 grams of oxygen. Then we convert masses to moles. So it'll be 4.151 grams of aluminium divided by the molar mass of, or the atomic mass of aluminium, which is 26.98, gives you 0.1539 moles of aluminium. And for oxygen, you do the same, and you get to the conclusion that it is 0.2308 moles of oxygen. So far, so good. You now have two numbers you can work with. So now you've got to find the ratio by dividing each element by the smallest number of moles. So in this example, 0.1539 was the smallest number. So you have 1 mole of aluminium and 1.5 moles of oxygen if you divide both those moles by the smallest number. Okay. So now you have a ratio. It's basically your ratio is going to be 1 mole of aluminium to 1.5 moles of oxygen. Okay, so now you've got to multiply by a common factor to get a whole number because you cannot have halves of atoms in compounds. So here the common factor would be by multiplying by 2. Oxygen would be 3 and aluminium would become 2. So the formula, therefore, is Al2O3, aluminium oxide, which is indeed what we see. So now we have that information. Let's see if you can do a problem. So you're given a 4.55 gram sample of cobalt and it reacts with 5.475 grams of chlorine to form a binary compound. Determine the empirical formula of that compound. So you've got 4.55 grams of cobalt divided by its atomic mass to give 0.07721 moles of cobalt and 5.75 grams of chlorine divided by its atomic mass to give 0.1544 moles of Cl. So that will be, the ratio will be the smallest, so the smallest number, of course, is 0.0721. Divide both by that, so we have 1 for cobalt and 2 for chlorine. So the formula is cobalt chloride. Another example here, find the empirical formula for a compound that's now containing 80% carbon and 20% hydrogen. So we no longer have masses, we have percentages. So what do we do here? Well, the first step is you can simply convert each percentage to grams. And all you do is replacing the percentage with grams. So it becomes 80 grams of carbon and 20 grams of hydrogen. And now we're going to work through the same steps. Divide each element by its atomic mass value. So you get 6.666 for carbon and 20 for hydrogen. Divide by the smallest, which is 6.666 for both sides, which will give 1 for carbon and 3 for hydrogen. Therefore, the empirical formula will be CH3, our methyl group. So here's another example to work out. Okay, so now find the molecular formula for the compound that was found to contain 80% carbon and 20% hydrogen. So now we're given a mass of the compound, total mass. It's actually discovered. So now we're not finding the empirical formula, we're actually finding the molecular formula. So how do we do that? Well, we add another step. We use the empirical formula to find that you just found CH3 and follow the method below. So step 6, divide your given molar mass by the molar mass of the empirical formula CH3. So we calculate the mass of CH3. Okay, so that's going to be 12 plus 3 times 1, which equals 15 grams per mole. Okay, so there'll be 30 divided by 15, which equals 2. So that's going to be the number we're going to multiply the empirical formula by to find the molecular formula. So CH3 becomes C2H6. And that's how we determine the molecular formula from empirical formula data. The final thing in the unit is calculating waters of crystallization. Okay, so when ionic compounds crystallize from solution, they often absorb water into their superstructure. And each mole of the compound absorbs the same number of moles of water. So we write this as the hydrated salt to show the water that's now been attracted to the compound. And these are examples here. So this is what the dot comes in, okay? That's what the dot is for. The dot essentially is saying that you've got 5 water molecules absorbed onto the copper sulfate crystal. So they're not part of the compound per se, they're just absorbed onto it. Okay, and how do we find the waters of hydration? Well, essentially what you do is you show the presence of water by slowly evaporating the crystals, okay, with a Bunsen burner flame. The water comes off, evaporates off, condenses in the test tube and drops out. And you can measure the mass of the water that's now been released. Okay, so what is the method? Well, here is the equation for copper sulfate, H2O, the hydrated copper sulfate. So hydrated just means that it has water in it. And then that forms copper sulfate, dry, and water. So you weigh out the empty crucible. You weigh the crucible and the hydrated copper sulfate, okay, with water. Then you basically heat it, and we heat it to constant mass. Okay, which essentially means that you are heating it until the mass remains constant. There's no more water on it. Okay, and then we're left with the anhydrous copper sulfate. So you're basically just heating the crucible containing the copper sulfate, which is hydrated, until it completely is removed of water. And then you know that because you weigh it and you get a constant mass. That means no water can come off. And then you weigh it again to see the mass now of the anhydrous copper sulfate. So now you have the mass of the anhydrous copper sulfate and the mass of the hydrous copper sulfate, and by difference you can work out the amount of water that has been removed. So usually in an exam you'll be given the data here, for example the mass of the empty crucible, the mass of the crucible plus the hydrated salt, and the mass of the crucible and the anhydrous salt. You can work out the mass of the hydrated salt by taking the mass of the hydrated salt and the crucible from the mass of the crucible, and you can work out the mass of the anhydrous salt by taking away the mass of the anhydrous salt plus the crucible from the mass of the crucible. Okay, and that will give us the mass of the water, because the mass of the anhydrous salt, the mass of the hydrated salt minus the mass of the anhydrous salt will give you the mass of the water, in this particular case 0.9 grams. And the molar mass can be calculated for copper sulfate as being 160 from your periodic table, and the molar mass of the water can be also calculated from the periodic table to be 18, and we can then use number of moles equals mass over molar mass. Okay, so it's going to be the moles of water will equal the mass of the water divided by the molar mass of water, which is 0.9 divided by 18, which is 0.05 mole. And then we have the moles of copper sulfate equals the mass of the anhydrous copper sulfate divided by the molar mass of the anhydrous copper sulfate, which is 1.6 divided by 160, which is going to be 0.1 moles. Okay, and then we have the ratio of moles of water to moles of copper sulfate, which is 0.05 to 0.01 or 5 to 1. So it means that the hydrated salt formula must be CuSO4.5H2O. And that's all you need for this unit.